What you see right here is the real P3 paper, May 2025. Just came out. Again, to keep the concept of my channel, I'm going to blind solve this paper without having seen it before. And I'm going to be timing myself as well. So I'm going to start the timer now. Okay, here we go. Number 1, functions. Okay, functions. Fx equals 2x over 3x plus 1. Gx is that. Find the value of g f1. Okay, this should be fine for most people. So f1 is just substituting 1 into the x of fx. And this is just 2 over 4, yeah, which is 1 over 2. And then we do that for gx. So we sub 1 over 2 into the g. We get 4 minus a half squared. So that would be 4 minus 1 over 4. Right? So that would be 15 over 4. That's the first one. Okay. Now I'll try my best because this is unofficial. There's no mark scheme yet, but if the mark scheme comes out, I'll just also post it in the description here. But there's no mark scheme as of the time of recording right now. B, find the range of f. Right. Now this is called a rational linear function. Yeah, very important. I've seen so many students make this mistake. So when you have the domain, the bounds for the domain, here is x greater than 0. You try substitute 0 into the function first. So what do you get? So f0 is 0, right? Because you sub that, you get 0 on top. But then if you look at the nature, so this is the first bound. The next bound you should get from the range is that when you look at the nature of the function, if you know that the rational linear function, the ones that looks like this, the range is only approaching a over c, right? Because if you substitute x to a very large number, say infinity, b and d will be negligible, so you will only be left with a times infinity over c times infinity, and that is just a over c. So the other bound of range here when x tends to infinity is the y will be equal to, like y is approaching 2 over 3. And when you got these two bounds, you write, you write them in the way that it makes sense. The smaller one to the left and the greater one to the right. And then that is just your range. So it cannot reach 2 over 3. It can be, however, 0, so we put an equal sign there. So that is the range right there. Yeah, that's done for part B. Part C, find f inverse. All right, so I'm just going to sub x and y, swap them. So this is x equals 2y over 3y plus 1 instead. And then you do what you should do. So 3xy plus x, just rearranging, equals 2y. We're going to extract the y. We're going to isolate the y. So we get just moving 2y on the left and then pull y out. We get this. And then put x on the other side. Yeah? No problem so far, right? And then y would be minus x over 3x minus 2. I just pull the minus out just for, aesthetics there. Yeah, mathematical aesthetics. Yeah. So this is the inverse. Now be careful because in P3 at least, every time they ask you to find the inverse, you should always, I stress, always specify the domain. Otherwise, you lose 1 mark here. Okay, so f inverse of x equals that. And then we write the domain. So the domain of the f inverse is just the range of fx. We already got that, right? So I'm just going to write this down, yeah? Wait, hang on. There's no equal sign there. Okay, just that. Yeah, I just took it from this. Exactly the same because we use the domain and range property there. So far so good, right? And now we solve. Well, this is also classic. You have f inverse equals fx, right? Well, if you think about the function, whatever it is, let's say this is my function here, and then this is fx. And then you are if you draw the inverse of this function, it's going to look like a mirror image. Yeah, I'm going to use a different color here. It's going to look like a mirror image, like that. This is the F inverse of that one, maybe. But then usually, it's not usually, always, they intersect at this very point. And that is on the mirror. And the mirror is y equals x, isn't it? So you know that whenever they write this and ask you to solve, you should recall that this is occurring at the x equals y, right? So you can just write, yeah, and this happens before in the past paper. I can just pick one of them and put it equal to itself. So for example, I can do 2x over 3x plus 1 equals x, because this is the y from one function, this is the x of that function. Or if you prefer, you can do 4 minus x squared equals x. That will also do. Let's do that then, right? Because it's quadratic, I don't need to do anything much after that. So I'm just going to start with that. And then rearranging, I guess, x squared plus x minus 4 equals 0. I can just solve this by, using a calculator, right? So, but I'm just going to do quadratic formula first. So minus b plus or minus square root b squared minus 4ac, like that. Actually, I don't need a calculator now. Seems like I've got everything. So minus 1 plus or minus, inside the square root, it's root 17. Because look, you have to write the working anyway, so if the numbers are not too bad to substitute, you can just do that over 2. Now, we need to be careful, because both fx and f inverse have a limitation of the domain. They're both greater than 0, right? This one greater than 0 for the f inverse, and the fx in the question already says that domain greater than 0 anyway. So if you happen to get a negative root and you put it, you're going to lose mark there. So I'm just going to say that the answer is just this, because that's surely greater than 1. All right, so that's it. That's my best shot for that. Wait, hang on. Yeah, that should be fine, right? Let me check. Yeah. Okay, I'm going to go with that. That's my best shot. Okay, so this is question 1 just done. Next, question 2 right here. In this question, you must show all stages you're working. Okay, fine. Okay, we can't rely on calculator technology too much. Okay, part A, number 2. That is a harmonic function right there. Express fx in the form of r cos x plus alpha. Okay. All right. So we should expand the thing first. Yeah. I mean, that's at least how I do it. Or if you want to remember the formula, that's fine as well. Then we get r cos x cos alpha. This is additional formula, minus r sin x sin alpha. Okay. Now the 7 cos x, yeah, if you compare the coefficient for both of them, then you see that the r cos alpha will be 7 and the r sin alpha will be 24. Yeah. So of course we can find r first by doing the Pythagoras for both of them, for both of the numbers there, and surely you will get 25 because I happen to remember 7, 24, 25 for the Pythagoras triangle. I prefer to get r first because usually you need to get r as an exact form. Alpha, can be in radians, and that's like 3 decimal places, and it's even saying here that r needs to be exact. So I got r first here, and then I just pick one of them, substitute r in. Like for example, alpha equals r cos 7 over 25 there. Yeah, just plug into one of them. If you prefer cos, you just go with cos. Sine, go with sine. Yeah. Okay, I'm choosing cos here. And then that's gonna require a calculator. Let me just bring one. Here we go. Okay, so r cos wait, how do we do in radian, so I need to change in radian first. Okay, r cos 7 over 25, that comes to be 1.3 decimal places. I'm gonna give it more first, like that, and then I'm gonna do that 3 decimal places. Okay, so that's my alpha right there. Hang on. Yeah. So yeah, so fx equals, now we're gonna put everything into the form 25 cos x plus 1.287. That's not greater than pi over 2, I believe. Yeah, that's fine. That's part A done. Part B. Using the answer to part A, find the minimum value of gx. Well, now we have gx to be like a modification of the fx, like a transformation actually. So we want the minimum of gx. And if you look at the function here, how do we make this minimum? You got to think about this, right? It's not always that, okay, like some students I teach, they go like, okay, if they want minimum, you put minimum fx or f2x here. That's wrong. That's not always the case. You got to use some logic here to think, okay, to make gx minimum, you need the denominator to be maximum. Yeah, follow? If you want denominator to be maximum, you make the subtractor here, if you like, the thing that you subtract here. You want the subtraction here minimum. Yeah? So this 3f2x term has got to be minimum. That makes the f2x minimum. Okay? And by minimum in this case, it also accounts for the negative sign. So the minimum of any cos or sine function would be -1. So minimum gx would be 5 over 90 minus 3 times -1 here, because that is the way that you make the denominator maximum. Okay, so that is just 5 over, what is that, 93, right? Fully simplified fraction. I got it. That's it. That's my I. That's bi. Now bii. The smallest positive value of x for which this minimum occurs. So you just substitute the f2x to be -1. I mean, it doesn't matter that you have the transformation in the x. It doesn't change anything. It's still a cos function. So that's why I put, wait, hang on. I made a mistake here. Sorry. I forgot that the whole f2x is not the same now. The 2x inside is still the same. I mean, hang on. Let me do this again. Sorry. Okay, so I'm gonna write the gx again. Yeah, gx. I forgot that you have the r there. Again, guys, this is a live walkthrough, so I might make a mistake along the way, but I'll correct it. f2x, because we got fx to be this, yeah? So f2x is 25 cos 2x plus alpha there. I'm just going to write alpha for now because I'm out of space here. Okay, so minimum g is then, you got to make this whole thing minimum, right? So as we discussed earlier, this needs to be -1, the cos function. So that would be 90 minus 3 times 25 times -1 right here. Still the same concept there. Okay. So that is 90 plus 75. So that is 5 over 165, isn't it? Just checking. And that comes to be 1 over 33, right? So that is a fully simplified fraction for the minimum. Okay, and that occurs for II, that occurs when cos 2x plus alpha equals -1, right? Because we put it as that. Okay, so we solve for this. Now, because x here, is there any limitation for x? it asks for the smallest positive value of x. So it's just like, you know, you need x to be greater or equal 0 here. Okay? So that means 2x plus alpha needs to be greater than, you know, alpha right here, where alpha is what? 1.287. I'm just modifying the range here so that I get the right angles. So if you look at the CAS diagram, yeah, cos of -1, well, how do we get cos -1? It's cos of pi radians. Cos pi is -1, isn't it? And it's the only one in the 1 period cycle there that gives you -1. So yeah, it's like this one. So it's pi or minus pi, but we need it to be greater than 1.287. So that's going to be pi there. So here I have 2x plus 1.287 equals cos -1. That is pi actually. So 2x plus that equals pi. Yeah, because cos pi is -1. And then x is pi minus 1.287 divided by 2. And they just want the smallest positive value for x. So that is just it. Okay, so that is my x there. Pi minus 1.287. Okay, so this is, wait, I probably need a more, that's fine, that's 28700. So I think I can round that. So this is 0.927 to 3 decimal places. That's it. So I think I'm okay with that. Let's go to the next one. Next question, number 3. Okay, I'm just going to move this bit up. All right. This is number 3. Figure 1 shows a linear relationship between log 10y and log 10x. Okay. The line passes through the points minus 3.50 and 0 minus 2 as shown. Find the equation linking the log 10y with the log 10x. They ask log 10y and log 10x and they give you a line. So according to the linear equation form here, you just change y to log 10y. Don't do anything else. The gradient, you find it by yourself. And x as log 10x. Don't do anything else. And the y-intercept here happens to be -2. They give you already in the graph. Well, what is the m? Okay, so the m is the gradient, which is rise over run there. So it's a negative gradient. So this is minus, what is that? -2 over 3.5, right? Yeah, it's a negative gradient. So I just put a minus there. Okay. And what is that? So if you simplify that, it's 4 over 7. Yeah, minus 4 over 7 there. I'm just checking my mental math. Okay, so I get minus 4 over 7 here. And that's it. The equation linking log 10x and log 10y. So that's it. So you just, maybe you can, I think I'm happy with that. I'm going to leave it at that actually. Yeah, so that's fine. And then that's part A done. Part B, hence or otherwise, express y in the form of an exponential like that. Yeah, so we took the part A answer to derive to an exponential form. So how do we do that? Well, we're going to just use a log property here. So if I, it's like we can reverse, we can undo the log 10 here by putting 10 to the power of on the right hand side. Yeah, so y equals 10 to the power of all that. Yeah, I'm just going to write it first. Now we can use the law of law of indices to split the power, right? So this is 10 to the minus 4 over 7 log 10x times 10 to the minus 2. Like that. Okay, so far so good, right? And then you can, you see that you can sort of like put the minus 4 over 7 here as a power of x right here, right? You can just pull the number to the power of x there because that's a log property. And the 10 to the minus 2 actually is just 1 over 100. So I can just write 1 over 100 here times that, because we need the p in front of x to the q. So we already got the p here to be 1 over 100, right? Now how do we do this? Well, another log property, if you have a to the log base a of x, that's going to be x. A to the log base a of anything is that thing, right? So this is 1 over 100, and looking on the right term there is just x to the minus 4 over 7. And I think we already got that. So that's done. So this is where p equals 1 over 100 and q equals minus 4 over 7. So I think I'm going to call it at that. All right. I can come back to check this later if I have time, but I'm going to keep the exam condition there, right, just to make it fair. The function f is defined by that, show that, blah, blah, blah. Okay, we need to simplify this, right? And if you paid attention to the IG math or the secondary math, you can factorize the x squared plus x minus 12. All right, just my first impression there. So you can factorize this to be x plus 4 and x minus 3, can you not? Because doing that means that you don't need to multiply too much. So for the second term here, you can just multiply the thing by x minus 3 and x minus 3 to make the denominator the same. Right? Now you can merge them. So that's 49x plus 7x squared minus 21x, just expanding everything on the right part. And then the bottom bit here is just, I'm going to keep it still the factorized form because we need to cancel out looking at the final form we want there. So simplifying all this, what do you get? Okay, seems like this will be 7x squared plus 28. I can pull 7x out, and this is x plus 4. Because 49x minus 21x is 28. And you can factor out 7x from both terms. Yeah? And that will cancel the bottom bit, right? Where you can cancel that. And that is as required. Yeah? That's it. Well, just going to keep writing x greater than 3 there, just in case, you know. B, hence find f dash x. So this is the derivative of fx, giving you answer in the simplest form. So we just need to differentiate. So seems like, how about a quotient rule, because there is a quotient of two functions here. Okay, so v du minus u dv over v squared. V, so hang on, I'm just going to do that first. So v du, so differentiate the top bit, we get 7, minus u dv, which is 1. So v du minus u dv, yeah, divided by the bottom bit squared. So that comes to be 7x minus 21 minus 7x divided by x minus 3 squared. And that finally turns to 7x cancel, so I get minus 21 over x minus 3 squared. Answer. Yeah. Yeah, the derivative. Yeah, that's fine. So we're good. I mean, it could have made it more challenging here to show that this is a decreasing function or something, right? But it doesn't. So we're going to keep on doing the next one. This paper is fine. I think it's not too bad. Yeah. Let's see. I mean, maybe the later question is harder. Okay. Integrate. Oh, this is classic. So you need to know that you need to make use of the double angle there. But this is, okay, the double angle, I write cos 2 theta equals 1 minus 2 sine squared theta. But the theta can be anything. So if you see sine squared 3 theta, yeah, you just change this to 3x. I mean, because you want 3x there. And that will also be 3x. It's effectively like you are substituting theta with something else. So our double angle would have been 6x instead on the left part. And this will be the thing you want, right? You got the thing you want. So if you rearrange to make that the subject, to make it clear, so you would have that. Just rearranging. Yeah? So, well, how about split? Because we're going to integrate split, yeah, to make it a little simpler there. There you go. And then integral sine squared 3x dx will just be integral of a half minus cos 6x over 2 dx. Yeah, it is indefinite integral, so we need to put a c after everything. Integrating 1 over 2 will just be x over 2. Integrating cos, we get a sine, so that's just sine 6x. Doing the reverse chain rule, we got to divide by 6, so we get 12 here instead and a c. Let me check everything again. Integrating cos, we get a sine. Reverse chain rule, 12. Everything is fine. So that's the answer to the first part. The second, 5II. Okay, this is also classic. It's a reverse chain rule, and if you haven't checked my video here, you go check video. This is just the tricky form in a reverse chain rule in P3. All right. So when you see something of this form, right, where one function is to the power of something, and in fact it can also be 1. So when you see one function to the power of anything, all right, and then when you differentiate the inner part, like inside here, yeah, that fx, and you get the thing outside. So as you can see, if you differentiate in the brackets, you get 2x. That is kind of like a factor out by a half. And that is fine. So when you get this, we should try differentiate the inner part. So if I differentiate the inner part, yeah, that's the inner part, the fx part, we get 2x, right? And we're going to make this the same as the outer part, which is just the x, by multiplying by 1 over 2, right? And we're going to keep this factor in mind. I got to be quick here. So if you want some more details, just go check the video again, yeah? Right? So that is the factor we need to correct later on. And when you see this form, you should try some correction factor, which in this case is the 1 over 2 there. And if x to the power of n plus 1 over n plus 1 plus c, of course. So that is like a reverse power rule, if you like. That means this whole thing, yeah, will be the correction factor k times the inner function, now to the power of n, which is 3 over 2 plus 1, right? It's just like a power rule here. So 3 over 2 plus 1 is just 5 over 2. You got to divide that added power as well here, and plus c. Okay, so flipping the fraction there, I get, so that will cancel with the 2 there. So I get x squared plus 4 to the power of 5 over 2 over 5 plus c. That's my answer there. Easy peasy, right? If you know how to use the technique here. Number 6. The temperature theta in Celsius of a computer processor t minutes after the computer is switched off is modeled by the equation that, where a and k are positive constants. Given that the temperature of the processor was 75 degrees when the computer was switched off, so that is basically t equals 0, okay? Find the value of a. Okay, so part A, so it's 75, we put 75 on the left part, equals 21 plus a times e to the 0, because t goes to 0 there at the start. This is called the initial condition. So A equals 75 minus 21. That should be easy. 54. All right. So that's my A there. Part B. Given also that it takes 5 minutes for the temperature of the processor to decrease from 75 to 25. So that is basically T equals 5, right? And then we want to find the value of K. Okay, so we just sub that in basically to 25. And this is 21 plus A is 54 already. E to the minus K times 5, right? So that's minus 5K. And we want to find the value of K. Okay, so 25 minus 21 is 4 over 54 equals E to the minus 5K. So if we want to find the value of K, we have ln of 4 over 54 over minus 5. Yeah? Okay, here we go. So let's do that. Fraction ln 4 over 54 divided by minus 5. Okay, so this is 3 significant figures, 0.5 to 0, 5, 7, blah, blah, blah. Okay, 3 significant figure. There we go. That's my K there. Let me double check. Yeah, I think I'm fine with that, right? Yeah? Everything is fine, right? Just checking. Yep, I'm fine. At time t, part C. At time t minutes, the temperature of the processor is decreasing at the rate of 9 per minute. Decreasing. Haha, okay. That's probably where people go wrong there. So you differentiate d theta by dt first. And then this is 21 goes to 0. So you have minus a e to the, minus a k, because we got to pull k down, and e to the minus kt. Just a chain rule there. Okay, let's see. So we got a to be a positive. Is this already decreasing? Yeah, there is already a minus sign. But it says decreasing at the rate of 9. You got to correct this. It's like, I mean, for those of you who do physics, well, yeah, or have done physics in the secondary level, deceleration is a negative acceleration. And acceleration is the rate of change of velocity. I'm just saying that when you say deceleration of 2, it is actually an acceleration of minus 2. What's the point? This is the decreasing rate of 9. It means that if you equate this to 9 without doing anything else, and then you put that to equal minus a blah blah blah, you're going to get this wrong. You're going to get an error, because you can't solve the log like that. You can try it by yourself. So rather than doing this, what is a again? A is 54. K is 4 over 54. And e to the minus 4 over 54 t. So you can't solve a log like this, because when you do the ln on the other side, you will see a negative number. It says a decreasing rate of 9. So actually, this is a minus 9, right? Because d theta by dt is a quantity that is a sign sensitive. D theta by dt, if it's a positive, it means an increasing rate. If it's a negative, then it's a decreasing rate. Now the question says a decreasing rate of 9. So you got to put a minus 9 here. And I believe this is where, for those of you who have done the paper, will get this wrong, I think. At least some of my students. Okay, so we put minus 9 there, and everything will be fine. Because now you get 9 over 4, a positive number, equals that. Yeah? So to solve for t, t will be equals to ln 9 over 4. Yeah? And then divided by minus 4 over 54. Right? Calculator. 2 decimal places, so I'm fine with that. Ln 9 over 4. and then go to the denominator, minus 4 over 54. Wait, what? I get a minus? Okay, hang on. Made a mistake somewhere then. Okay, this shouldn't be a minus. Let me check, right? I think K is fine. K is fine. A is fine. Decreasing rate, minus 9. A is 54. I'm just checking everything. Wait, hang on. Yeah, that's the same, right? I mean, it could have just been that and that, right? At the beginning. Yeah, sorry. Same thing. Wait, oh no, the derivative is it has a minus. Sorry. Yeah, it has a minus at the start because we differentiate minus k down. Yeah. Sorry, that was right. And then I put in. I'm just checking. I put in 54 here. K was. Oh, I got k wrong. Sorry, guys. I misplaced k here. That is not right. I'm gonna keep everything as k first because I got k earlier. Wait, you gotta be careful here. Okay. This is k. Okay, let me redo that. Okay, so that should be right. A k e to the minus kt. All right, so what do we want here? Okay, 9 over 54k equals e to the minus kt. So that means ln of 9 over 54k equals minus kt. So t is equal to ln of 9 over 54k divided by minus k. I'm going to be careful there. So what is our k again? You see, I already put down to quite many significant figures, so I think I'm going to do 0.52054 here. Keep that as an answer, clear. And then I'm going to do that ln 9 over 54 times answer. There you go. That big guy right there. And then minus answer. That's minus k, right? Yeah. So I got 2.187864 blah, blah, blah. Yeah. And we want into 2 decimal places. So that is 2.19 minutes. That's it. Okay, I think I'm happy with everything here. Let's do question 7. Question 7. A continuous curve has equation that the curve has a stationary point at point P. Show using calculus x coordinates of point P is a solution to the equation. That's fine. We differentiate first because it's about stationary point. dy by dx. This is a product rule, but you got to be careful. So u dv, differentiate sine 3x, so I get a 3 outside here and a cos a 3x, right? Plus v du, so I do a du first maybe. So du I get, so when you differentiate an exponential function, the first thing you do is copy paste the whole exponential. And then you differentiate the power there. Differentiate minus x to the power of 2 is just minus 2x, right? So I'm squeezing in here. So it's just minus 2x. So that's why I turned this to a negative. Yeah? And then sine 3x kept the same like that. Okay. And now, because we want the stationary point, we equate this to 0. So I do 0 equals, while also taking e to the minus x squared out. Okay, with the trig function inside there. That is 2x sine 3x, right? Yeah? Everything's good? All right. So how do we do this? Well, e to the anything always greater than 0. That means we can cut that out. Yeah, just divide that across both sides. And if we move 2x sine 3x to the other side, we're going to get this equation right here. Well, I see tan there, so I'm going to get a tan. So 2x over 3, oh wait, hang on. Should be the other way around. So sine 3x over cos 3x equals 3 over 2x. Just deriving here, dealing with the algebra. So tan 3x equals 3 over 2x. That means 3x is arctan 3 over 2x, right? And then x equals 1 over 3 arctan 3 over 2x as a required. Okay, that's part A, right? Part B. Use iteration formula. That first thing, x equals 0.4. Now I think I'm gonna have to use a different calculator. Okay, here we go. I'm gonna use this one because this one is better at iterating. So we need to put 0.4 as an answer first, and then 1 over 3 times, yeah, zoom out a little bit, arctan. So arctan, that's in degree. I need in radians. I need to put in radians. Hang on. Let me check something. If I do, I always check this because I'm not sure. Okay, sine of pi. Yeah, I get 0. That makes sense. All right. So what's the answer again? 0.4. Okay, so 1 over 3. Wait, that's not. 1 over 3. Zoom out a bit. Times arctan. Oops. 3 over 2 times answer. That's the first iteration. I'm just going to write that. Just for some working there. So this is 0.4367, 4 decimal places, right? And then for the second one, if you press enter once, wait, hang on, was it the same one? If you press the enter again, you're gonna get the third one. If you press it again, you're gonna get the fourth one. I'm gonna need to check this again because I didn't see what happens when I did. Okay, you know what? I'll do 0.4 again, equals, that's the answer, yeah? Okay, and then again, 1 over 3 times arctan 3 over 2 times answer. Zoom out a bit. Okay, I haven't pressed an enter yet, but it already gives me the answer. So that ends with 682. Okay, so that doesn't change yet. So this should be x2, and this should be x3, and this should be x4. So I got it right. Okay, so that's x4 there. Okay, just move everything to the left a little bit. There. Okay, that's x4, 4 decimal places. Check again. Yes. C. Using a suitable interval and suitable function which should be stated, show that the x-coordinate of P is 0.430, correct to 3 decimal place. Okay. Okay. Let's try this interval. Now, you got to be careful. This question can be tricky. Which function are you going to substitute these two bounds in? Is it the y function or is it the derivative function? Because we want the answer for the x-coordinate of P, and P is a stationary point. So you should take the derivative function, which is this guy, and not the y. And I bet that this is where most people get it wrong, because they will just use the y, and And yeah, strangely, they won't get a change of sign, and they will be shocked. Oh, did I do calculator work wrong? And they will spend valuable time doing that, just checking, but it's already wrong at the beginning. So you don't make this mistake. All right, guys? You use the derivative function here. Now, actually, it's this one. So I'm going to take the liberty of copying that and pasting here. Okay? So that is df dash x, or let me put it to just some new function gx, and then we're gonna do g 0.425 here and g of 0.435 and see how that goes. Okay, so I probably need to put some x as an answer first. So like now I'm gonna bring back my better calculator here, I think. So what was it? 0.425, put that as an equal and clear, and then 3 times, where's e? E to the power of minus answer squared. Yeah. All right. Put it down, times, this is already in radian, cos of 3 times answer minus 2 times answer times e to the power of minus answer squared. Okay, and then times down here sine of, let me check the sign, 3 answer, and that should be fine. 0.051270 blah blah blah. Let me just check everything if I put everything correctly. I'm very careful because of course there's no mark scheme yet as of now. Yeah, that's fine. Cos 3x minus 2x e to the blah blah blah, so everything is fine. Yeah, I'm thinking I'm happy with that, but just one thing. I'm just curious if I do minus 3 squared. Yeah, it gives me minus 9, so that's fine. I'm fine. I'm good. Oh, I still do another one. Okay, hang on. Okay, the next one is 435, right? So 0.435 equal, and that's stored. So start over again. 3 times e to the minus answer squared. Squared here. Sorry. Wait, I'll do that again. Answer squared. Wait, where's the minus sign? Minus answer squared. Yep. Times cos 3 answer minus 2 times answer times e to the power of minus answer squared and times sine 3 of answer. Okay, I get a change of sign, guys. Applaud. All right, here we go. So there is a change of sign in gx while being continuous in the interval I chose that. So the x coordinate of p is 0.4430 to 3 decimal places. Yes, that's it, number 7. Number 8. Part A. Prove that blah blah blah. Well, this is typical. Never thought that it would come up with this one, but it's in one of the past paper. Okay, so you just use the tan A plus B additional formula twice, I guess. So maybe you write first tan 2x plus x here. Yeah, that's tan 3x. And then we're going to do, so if you look at the formula, let me show you the formula. Yeah, you can look at the formula there. Okay, so let's look at the formula of additional formula of tan. That's going further there. Okay, we're just going to use this one. So if this is a plus, the top will be a plus, the bottom will be a minus, right? Just understand that notation there. Okay, so this is tan 2x plus tan x divided by 1 minus tan 2x tan x. Okay, and then you write here maybe tan 2x equals, well, tan x plus tan x, that's 2 tan x, divided by 1 minus tan x, that's tan x squared, and we're going to sub that into the tan 2x. So this is 2 tan x, just using this, yeah, divided by 1 minus tan squared x plus tan x, all divided by 1 minus, again subbing that in, 2 tan x, divided by 1 minus tan squared x times tan x here. Yeah? Alright. So it looks like this is the denominator that will cancel. So we're going to simplify the top part and the bottom part separately, and those two denominators will cancel. So that's 2 tan x. Well, if you multiply this to make the denominator the same, we get this, right? And then, yeah, you can write that, I guess. That's fine. But this is a bigger fraction down here. And then 1 minus 2 tan. Wait, that's, if you multiply that, that's going to be 2 tan x squared. And then if I also do the denominator, multiply this into that, I get 1 minus tan squared x, and then minus 2 tan squared x, multiplying everything in, and the same fraction here. Yeah? So the two denominators cancel, and then I simplify the top part, right? Just slowly here. Expanding everything, and the bottom part will be 1 minus 3 tan squared x. Okay, I think I got everything. So that's 3 tan x minus tan cubed x divided by 1 minus 3 tan squared x as required, right? Yeah. And yeah, of course, we can write x not equal to n plus 1 pi over 6. That is just saying that the bottom bit cannot go to 0, basically. All right? Just keep with the flow there. Hence, solve for that, for part B. Okay, so if you look at the part A here is exactly the same, just turning x to a theta, right? So this, we can turn the left part here to tan 3 theta, right? Equals 2 sec squared 3 theta minus 8. Yeah? And now let's deal with the bounds first, because I'm always cautious about the bounds. Otherwise, you will, maybe not get all of the answers or get more answers than you should. So if you multiply the whole domain by 3, you get 0 less than 3 theta less than 3 pi over 2. All right? Okay, just for the sake of solving cast a diagram later, right? Okay, so here we have a sec squared and a tan, so let's turn that into a tan using the identity. So sec squared is 1 plus tan squared, right? Like that. Yeah, I'm happy with that. And then this is 2 plus 2 tan squared 3 theta minus 8. So 2 tan squared 3, that's my tan squared 3 theta, minus tan theta minus 6 equals 0. Let's see. Yeah, I'm happy with everything. And can we factorize this? I would like to factorize, would I not? Hang on. Let me try that. So if I put a 6 and a 1, doesn't work. A 3 and a 2, yeah. 2 here, 3 here. Yeah, I think that's fine. Okay, so we're going to solve for these two brackets. So it's tan 3 theta equals minus 3 over 2, or tan 3 theta equals 2. Both cases work because there's no limitation for tan. It can go anywhere. It's not like sine and cos where you have 1 minus 1. Okay, so for this one, it's a tan of a negative value, so you having this 2, 1, okay? For this one is this one, yeah? But for the first one, the principal angle or the basic angle can be found by just doing, arctan 3 over 2. I take the negative out. Yeah, that's my principal angle. I'm going to use a calculator. So arctan 3 over 2 there. We are doing in radians, so this is already in radians. So arctan 3 over 2. I got, going to write it first, 0.982793 9827937. Okay, yeah, so let's do for that one first. Now the basic angle here will be that one and that one, right? So that is the size of the basic angle that I got. But okay, the bounds of 3 theta here is from 0 to 3 pi over 2. So 3 pi over 2 is just about quadrant 3, at the end of quadrant 3, right? So I guess it's just this one here. And that's it, because you can't go greater than 3 pi over 2. So 3 theta here is just, and that's a negative, yeah. Okay. Pi minus, let's say this is alpha, yeah? Pi minus alpha. Okay, and that's one of them. And just one, I think. So I'm just going to do pi minus that, just to keep it exact. Okay, so that's 2.158798, blah, blah, blah. And if you divide that by 3, you're going to get theta. And this is the only answer. We need 2 decimal places. So 0.72. Yeah, that's one of them. For this one, we do arctan again, 2. So I'm going to do arctan 2. So that's the principal angle there. Yeah, that's the principal angle here. Now, we might get more than one answer here. At least we get the first quadrant answer, because 3 theta, can be in quadrant 1 or 3, right? So this is one of them. 3 theta equals 1.107148. Yeah. And I'm just going to make 9 here. And we do pi plus this, so plus pi. So the other one is that. Okay, so theta equals, so I'm going to do first one first, divided by 3, I get 0.37. Yeah, and the other one, if you, if you do brackets arctan 2 and then plus pi, yeah, That's the other one before dividing 3, and now divide by 3, I get this. Yeah. So that's 3 answer, right? I'm just going to conclude down here. So theta equals 0.72, 0.37, 1.42. And none of them are beyond pi over 2. Pi over 2 is about 1.67. Yeah, so I'm fine. All of that would be my answers. Okay, number 9. I'm at an hour, so I think I'm still fine. This graph looks intriguing. Figure 2 shows a sketch of a curve C with equation that the curve intersects y-axis at A and B, as shown. Find the exact value of y-coordinates for point A and B. Okay, this is like an inverse function, right? But we already know that for point A and B is when x equals 0. So 0 equals sine of all that. Yeah, it's like an inverse function of sine here. It's like a, a wave, sine wave on the side. Okay, so we are solving sine 3y plus pi over 4 equals 0. And we're going to get y there. Now, we got the range of y, so we got to be careful here. It's a trig again, solving a trig again. Because we have pi over 12 less than y less than 3 pi over 4. So if we multiply that by 3, we're going to get 3y first. So that's pi over 4. And this is 9 pi over 4. Just multiply everything by 3, yeah? And then you plus pi over 4. So the right bound will be 10 pi over 4, which is actually 5 pi over 2. Right? And the left bound will be 2 pi over 4, which is pi over 2. So that's beyond the second quadrant. It's second quadrant and then up to the first quadrant of the second cycle, right? So we're going to solve this, yeah? So 3 pi plus pi over 4 will arc 0. Arc sine 0 is just 0. But 0 is not in the bound, so we got to use pi, right? Yeah. The first one after 0 is pi, and then we also have 2 pi. 2 pi is still in the range, and that's it. That's it, because we can't go more than that because we are at the bound of 2.5 pi there. So I'm just solving y here, basically. It's just pi minus pi over 4 over 3, or 2 pi minus pi over 4 over 3. That's 4 over 4 minus pi, 3 over 4, so that's pi over 4 there. And that's 8 minus 1, 7 over 4, so that's 7 over 12 pi. Okay. I think I'm happy with that. 3 pi over 4. Yep. 8, 7. 7 over 4. Yep. I think I'm good. Now, exact value of y-coordinate of A and B. Yeah. So A. So I'm just answering here y because A is below. So we go for pi over 4. And y for B is 7 over 12 pi as well. I almost forgot the pi there. That's it for part A. Part A here. Part B. Show that dy by dx overall squared is that. So because we are getting the function x as a function of y, so we're going to do dx by dy. Yeah? We're going to do dx by dy. So this is just a standard formula. You just differentiate sine, you get a cos, right? You keep the angle the same first, right? Don't do anything to it yet. And then chain rule the argument of the angle. So you differentiate, you go inside and differentiate respect to y, so you get just 3. Right? So that is just 2 cos 3y plus pi over 4. Yeah? Okay, so that's dy by dx by dy. So that means dy by dx squared, right, would be 1 over, I'm squaring that, putting it down here, cos squared of that, everything. Okay, so that's dy by dx squared. Now we got to put this into a polynomial form. Seems like they don't want any trig function here. Now we got the x. If you look at the x function here, if we square both sides, yeah, we're gonna get 4 over 9 sine squared of 3y pi over 4. Now, but this is what? A sine squared is a 1 minus cos squared, right? Identity works for all types of angle. As long as they are the same, we can just put 1 minus like that. Trig identity, yeah? So the point I'm doing this is because I want to get rid of this guy, the cos guy, right? So if we make cos the subject, yeah, I'm doing it. Just putting the 9 over 4 on the other side first. So cos squared, actually I should have, yeah, okay. Look, I'm just going to do 9 here. Just the 9. I'm going to keep the 4 here, yeah? Because we have the 4 cos squared there, right? So here I have 4 cos squared as a subject, right? And then this is 4 minus 9x 4, x to the 4, yeah? And that's it. So dy by dx overall squared would be 1 over. Just substitute the whole thing here there. So this is 4 minus 9x to the power of 4. Wait, how come I get the power of 4 there? This is 2. Sorry. Because that was weird. And am I fine here? Just double checking. I think I'm fine. Yeah, I'm gonna, wait, what? Square here. I'm very careful, guys. Okay, yeah, I think I'm happy with this. Am I? Yeah, I got the same there, same form. Part C. The normal to C at A and the tangent to C at B intersect at point D. Horrible. We need to find two functions. The answer to B, using the answer to B and the sketch of the curve C in figure 2. Okay, they intersect the point at D. Okay, so what happens here? Normal to C at A. Okay, so I'm just going to draw my own graph here. And then I'm going to maybe draw a rough shape. Okay, let's see. So they say normal to C at A. So I'm going to maybe have this kind of line here. I hope that's normal. Let's make a different color, yeah? And then tangent to C at B. Tangent looks like this, yeah? Let's see. Let's make it a little... Okay, here we go. Okay, so they intersect at point D, so around here. Let's hope that's not on the curve, right? Okay, so what do we do? They say using the answer to part B. That's dy by dx squared. So that's going to give us the gradient. Okay, yeah, we'll use it. All right, I'm just checking which one is the quickest way to do this. But okay, so dy by dx at, we got the x coordinate here. I see. So the x coordinate of point A and B is the same as 0. Right. Okay, that's why they tell you to use that, because you got to figure out which one makes sense. All right, so this is square root of 1 over. P is 4 minus 9 of 0. Yeah, this is 0. So that's plus or minus. Okay, that's interesting. I only get one answer here. Oh no, I get 2, so this is plus and minus. Right. Yeah, I do get 2 gradients. And now they tell you to use this because you got to figure out which one is A and B. If we draw the tangent at B, it's going to be a positive gradient. If we draw the tangent at A, it's a negative. So, well, m of tangent at A is minus 1 over 2. And the m of tangent at B is plus 1 over 2. Right. Okay, we are fine. But they want the normal at A. So that means we use m of normal at A here is just flipping the fraction and put a minus sign. We get a 2 here. And then find the simplest form, the x coordinate of D. Yeah, I hate to say that we might need to do 2 functions. Is there a better way here? Hang on, let me think about that. Probably not. Okay, I'm going to go with that. So y minus y1 equals mx minus x1. We're going to use this for both lines. So for the normal, y minus y1, this should be at point A. So point A, y1, ya is, where's ya? Pi over 4. Pi over 4 minus m is 2, x minus x1, 0. So just 2x, right? And the other one is y minus y1, which is the y of b, which is 7 pi over 12, equals m, which is 1 over 2, times x, because x1 is also 0. And now we equate these two. We want the x coordinate, so we should keep the x, so we make y the subject. So this is y equals 2x plus pi over 4, y equals 1 over 2x plus 7 pi over 12, and we equate the two. There you go. And yeah, the answer should be the x coordinate of D. So simplifying the x term, we get 3 over 2x here, and we move that. So that is just 3 pi all over 12 there. 3, yep, I think I'm okay. 3 over 2x equals 4 pi over 12. And that is just basically 1 over 3 pi. So x equals 2 over 9 pi. Really? Interesting. Okay. Okay. I'm just gonna keep that. I think I should be happy with that. And now the last question, question 10. Oh, okay. I'm at an hour and 12. I'm fine. I think I'm fine. Oh, the last question already. Figure 3 shows a sketch of a part of a graph with equation y equals fx, where fx is modulus of that, and k is a positive constant. Nasty. The graph cuts the y-axis at point A and has a vertex of point P. Okay, so you don't know k here for the time being. Find in the simplest form in terms of k. Okay, part A. The y-coordinate of A in terms of k. Yeah, so y-coordinate, we can do that by sub x equals 0. So x equals 0, y would be absolute 10, absolute minus 10 is 10, so that's just 10 plus k, right? Yeah. And then the coordinates of P, so we got x and y. Well, that's the vertex, so you put the modulus equals 0, so you get x equals 10 over k, and the y would just be the k. So P here would be 10 over k, comma, k. Straightforward. B, find in terms of k the range of values of x for which of x which satisfy that inequality. Now, of course, guys, in P3, when you have the graph, you use the graph. I always say that, I think, every walkthrough. So here we have the modulus function being on the left part here, greater than the 2k. So if I were to draw the shape quickly here, I would get that kind of shape. And this is somewhat kx minus 10 modulus and plus k. Yeah, that's fine. And now we have another line 2k, which is a bit less steep. So actually I should draw that a little more steep, because then I can draw the other one easily. Okay, moving a little up. And then the other line will go like that, less steep, like that. 2k. Wait, hang on. That's not less steep, that's more steep, that's steeper, that's 2k. I can undo that, hang on. Okay, so that's more steep, like that. And this is why you should use the graph. Do you see that logically they intersect at one point? So if you blindly solve this algebra by not looking at the graph, you'll get two answers. Yeah, you'll get two intersections, but they only cut at one point right here. Let me just confirm that, right? So is the x here and you got steeper? Yeah, it only cuts at this point. So what? Well, it's the negative gradient of the wing of the V shape, and it's the 2k actually. Yeah. So we just pick the, oh, no. This is not 2x. I thought it was 2x. This is 2k, guys. Okay. Let me start over again here. 2k is a constant, so it should be a horizontal line. This is a k, and where is a again? A is the y-coordinates of a is 10 plus k. We don't know what k is, right? Okay, so whatever 2k is, we need to make it at critical here because we want two distinct points. So it's from this point and upwards, right? So it's got to be greater than that. At critical, wait, hang on. This is where it cuts once, so that's just what we want greater. Wait, sorry, this is question B. Okay. Yeah, sorry, it's just that. Okay, 2k is somewhere there. All right. So yeah, we have two intersections here. So we're gonna solve separately. So kx minus 10 plus k equals 2k, and kx minus 10 plus k equals minus 2k. All right. Wait, no, it should be, no, not that. It should be a negative of that. So minus kx plus 10 plus k equals 2k, not that, sorry. You put a minus sign in front of the whole modulus term. All right, so this is kx minus 10 equals k. And then we want to solve for x in terms of k. So x is k plus 10 over k for this one. What about the other one? Well, it's minus kx equals, interesting, yeah, k minus 10, yeah, divide by minus k. So if I make k the subject, sorry, x the subject there, right, or 10 plus k over k, yeah, no, 10 minus k. All right, so I think I'm happy with those two x's. Yeah, I think I meant part C there when I said about two intersection there. Okay. Oh, hang on. Part B, they want a range. Okay, I'm not done here. I'm not done. Sorry, I got to put in the range. So this is the part where the V shape is above the line. So you go lower than this one. or greater than this one, right? So smaller than this one and greater than this one. Well, which one is smaller? Actually, this one is smaller. Oh, good that I double check actually. So this one should be smaller, and if k is a positive constant, the sense is that this one should be smaller, right? Okay, so x less than 10 minus k over k, or x greater than k plus 10 over k. Am I happy with that? Hang on, let me check. And that is greater than or equal, so we gotta be careful. We need that as well. Aha, don't forget that. This question has taken some time now. Okay, part C. I'm going to go part C now. Okay, part C. Given that the line with equation that intersects the graph at two distinct points. Okay, now again. Got the V shape, and now this is where the line is steeper. Yeah, I probably looked at this one and thought that it was steeper somehow. And yeah, we talked about this before. The line is steeper, and as you can see, it cuts the V shape only at one point. Okay. Wait, hang on. The line should be a little up because this is 1. But the steepness is the same. So this is at 1. Okay. The range of values of k again. Okay. Wait, what? Two distinct points? I'll take that back. Two distinct points. How come? If x is that. Oh, because we don't know what k is yet. Right. Yeah, guys. Okay. Yeah, we don't know what k is yet, so the gradient might be... Okay. Now I get it. So this one is fixed, yeah? It's a fixed gradient. So if the V shape is like this, and this is assuming that the right wing of the V shape is the same gradient as the line. It only cuts once, right? Now to make it cut 2 points, the V shape must be steeper. So they're going to cut somewhere above here again, apart from this first point, right? This first point right here. Yeah? So that means the gradient of the V shape must be greater than k. Greater than 3, right? So k must be greater than 3 for the V shape, isn't it? And so k must be greater than 3. I'm just going with that first. And we want the range of value for k. Okay, so k greater than 3, can it be... What is the upper bound? So if we have a look... that's fine, there's no upper bound here, but this is just by considering the slope. Now, two distinct points. Interesting. And because this is at k, right? So there will be some case where if you have k too high, yeah, too high like this, you're only going to cut at one wing, the left part. So k must be low enough. K must be low enough so that the vertex here is below the line, right? So we consider here this point, the vertex of the V shape. What was it again? We got it earlier, which was 10 over k, comma k. Now, to make the vertex of the V shape below the line, so that apart from k having to be greater than 3, so at the vertex here, the k value must be lower than the y value of the line. So if you look at the same x value here, which is 10 over k, whatever the y value of the line, it has to be greater than the y value of the vertex. To make them see each other again, you know, at somewhere above there. I'm going to make this steeper again. Yeah, because if you think about it, if this is above, they're not going to meet again. So we need to make this below, right? So that's my logic there. So if we bring the line equation, we put y as k and x as 10 over k plus 1. This is at critical. We make them meet each other here at this point first. And we're going to say that k has to be below that, right? K has to be below that. So what is k here? Okay, this is quadratic. Okay. Right. They would like to, you know, do that to you. I see. Okay, so from my knowledge of algebra here, this is k minus 6, k plus 5. So k is 6 or minus 5, but we want k greater than 0, so we're going to take k as 6. And k have to be smaller than 6, because if you have k greater than 6, the V shape will be above. And they're not going to meet again. So we need the V shape to be below, so if we put everything, okay, can k be 3? Well, can k be 3 again? No, because that would be parallel if we move the line down. Yeah. So we have k greater than 3, less than 6. I think I'm going to call it, because that's the last question. I guess the feedback here, the first, because I don't have any mark scheme, this is just a new paper. I think the first 5 questions are fine. Number 6 here could be tricky if you don't take care of the minus sign here. This one is also kind of tricky. If you use the wrong function for the numerical method, they have been talking about the x-coordinate of the turning point. So you need to use the derivative function and not the y function. This one, well, just learn how to derive the tan 3x here. This one should be fine. Be careful with the cast diagram. This one is a real deal here. You need to know that this is just x equals 0. I mean, it should be fine. Maybe not for some other people. But this one might take some time. Okay, you got to be careful. This one took me quite a while to finish, because I got confused at B and C. You know, I thought C was B and B was C. Okay, and that was probably it. I think I made it in time. All right, guys, because we have no mark scheme yet, so I think I'm going to write something in the description if I found my mistake earlier. Later. And I hope that was all useful. I'll see you in the next one. Bye.